the level of the topic which I am going to cover today is little higher than we are accustomed with the undergraduate studies. So only if you are really interested in finding the actual model of the synchronous generator and you want to devote some time in the in-depth study, then I suggest that you should watch this video. Otherwise you can pass over this video. After my lecture number 90 regarding the equivalent circuit model of a synchronous generator on fault when it was already carrying some load before the fault happened, I am getting a lot of queries. How did we arrive at the equivalent circuit model for the synchronous generator in that scenario? Although I have tried to give some explanation in that video also, and the explanation which is appropriate for the graduate level was given in that lecture, but since I am getting so many queries, so I thought that I should give the detailed mathematic background for the derivation of that model. So let's see how to derive that equivalent circuit model of a synchronous generator when it is carrying a load and then fault occurs on it. Before starting to study the synchronous generator for that scenario, we should know that as we have seen in a salient pole synchronous generator or synchronous machine, we have two things. One is d-axis and the other is q-axis. So what we will do, we will try to form an equivalent model of a synchronous generator in terms of two reaction theory. This theory was first proposed by Park, then it was further improved by various researchers and scholars, and today what we will study the Krone's primitive machine. So it can be proved that any machine, any general machine, whether it is AC or DC, except few special machines, can be shown as an equivalent machine with the windings on two axes, the d-axis and the q-axis, similar to the two reaction theory which we have already seen in our machines course when we studied the salient pole machines for the synchronous machine part. So what does the Krone primitive machine means? Krone is the name of the researcher. Okay. According to him, the synchronous generator or synchronous motor can also be represented by a primitive machine with windings on the d-axis and the q-axis. We already know that the d-axis is, if taken in this direction, then q-axis will be 90 degree away from it. So let us say it is q-axis. Let us say this is the field winding. I have connected a DC source in the field which is giving a current IF, creating some flux. Okay. Now the armature winding, although in a synchronous machine we know that the armature winding is distributed and multi-phase, that is there will be distributed winding for phase A, phase B, phase C. Okay, and the number of poles can also be more than 2, but we know that in any machine the pattern repeats with the number of poles. So anything which can be explained with two pole machine can be explained by multiple pole machine also. So what we will do, we will show the equivalent armature windings on the d-axis and the q-axis. Okay. Although the proof I will not cover in this lecture, it can be easily proved either using the Park's transformation or by using various mathematical tools, that the phase quantities IA, IB, IC can be transformed using some transformation matrix in terms of the d-axis quantity, q-axis quantity, and a zero sequence quantity. This zero sequence is the same which we study in the symmetrical components whenever we study the unsymmetrical folds. Okay, so either we can directly use this transformation matrix and find various values. Now, since we are going to deal with only the symmetrical scenarios, that is load is symmetrical or the fault is symmetrical, so this thing is not going to come into the picture. Okay, so instead of writing the Parkes transformation matrix or any other mathematical model, what we are going to do, we are just assuming that yes, we can show the three-phase distributed armature winding in terms of two windings, one which is on the D axis and other is on the Q axis. Let us say here a voltage is being generated VQ and this current is being given to the load IQ. Similarly, this current is ID and this voltage is VD. Okay, these are AC actually. This plus and minus is showing the instantaneous at some point of time. Okay, now there is a term called pseudo stationary. You might have seen while during study of the DC machines that the armature flux in a DC machine is always stationary in space. Usually in a DC machine, what happens, there are poles and there is this armature with the various conductors. Okay, so the field created by the armature is also stationary in the space. These poles are stationary, so these poles will create a stationary field. Similarly, even if this rotor is rotating, the flux created by the armature reaction is stationary in space. Okay, so by the meaning of this pseudo stationary, what I want to say, even though these windings are rotating on the rotor, okay, but the flux being created by them is stationary in space. So this is one thing. Now next we will come to the sign convention. Usually for the Krone's primitive machine, it was given that currents will be, towards the center of the rotor, the winding end towards the center of the rotor will be having a current inside the coil. Instead of this direction, it will be having a current inside the coil. Similarly, this will be having a current inside the coil, and this is already having a current inside the coil. So that direction was taken as positive. But here we are taking a case of generator. So what I have done, I have just reversed the sign convention. Usually in the study of the two in this study of two-axis theory, we deal with the motor part. Okay, but since we are going to study the generator, that's why I have just reversed the sign convention. This generator is feeding some load, this generator is feeding some load. Okay, according to the Parkes sign convention, whenever a positive current is being flown into the winding, then it is going to create a flux towards the outside along its axis. So this winding will create a north pole here and south pole here. But since I have reversed the sign convention here, so instead of creating a north pole here, this winding will create a south pole on the surface of the armature. Similarly, this winding will also create a south pole on the surface of the armature. So instead of showing the direction of currents and all those by using dots and cross and other things, what I have done, I have taken a sign convention in which whenever there is a current flowing in the positive direction, what was the positive direction? The direction was assumed positive whenever the current was entering into the coil towards the center part. Okay, but here since I reversed this direction, so the field will also be reversed. So in this way, what I have done, I have tried to show the creation of various poles on the armature as well as the field. Okay, now what I will do, I will try to write the equations of the voltage in various coils. Before that, we should know that in a rotating machine, there are two kinds of voltages which are induced. First one is the transformer voltage. Second one is the rotational voltage. Okay, the transformer voltage will be there whenever there is no motion. When there is motion, it will also be there, but this voltage will only be there whenever there is a relative motion. Okay, now whenever the distribution of flux density is sinusoidal in the space or in the air gap, then it can be shown, although I am not going to prove it here, it can be shown that the various inductance coefficients used for the transformer voltage and the rotational voltage will be equal. So what I will do, I will take these inductance coefficient by assuming that the flux density distribution is sinusoidal to be equal, and that we will see when I am going to write the equation. Now let us write the equation for the various voltage in these three coils. First the field coil, Q axis coil and the D axis coil. So up to now what I have done, I have just told that any machine, any general machine can be drawn in an equivalent form with winding on the D axis and the Q axis. Like if it had been having some damper winding also, in this thing I have not considered the damper windings. If I had considered the damper windings, then damper windings could also be shown on the D axis and the Q axis. Okay, so to reduce the complexity, I have not shown the damper windings here. Now let us write the voltage equations. That we will do in the next slide. Now let us write the equations for the various voltages. The applied voltage Vf can be easily written as the resistance of the field winding into the current in the field winding plus the inductance of the field winding d by dt of the field winding current. Now in writing these equation, I will write d by dt as the operator P. Okay, so I will write it as P here. Okay, now the flux created by the currents, the load currents in the armature will be stationary. Okay, so there will be no rotational EMF in the field winding, but there will be a transformer EMF induced in the field winding. Okay, now this is south pole, so the flux will be like this, and this is again south pole, this flux will be like this. So you can see that these two are opposing. So I will use a negative sign here, and this is the mutual inductance coefficient d by dt of the current in the D axis armature winding. Okay, now you might be wondering why I have not used any current of the Q axis. You can see that the for transformer voltage, the mutual inductance between the two windings Q and D is 0. Mutual inductance varies according to some law, M plus M1 plus M2 cos, or rather it is directly varying with the angle of theta, where theta is the angle between the coils. Okay, so this theta is 90 degree here, so this mutual inductance is 0 between the Q axis and the D axis coils for the transformer voltage. Any voltage which can be there will only be the motional EMF. Okay, so this is the first equation. Now let us write the voltage for the Q winding. Here it was the applied voltage, now it is the generated voltage. Okay, now this VQ cannot have any transformer induced voltage because of the currents in the D axis. It will be having only the motional EMF because of the currents ID and IF. Okay, but let us say some current is flowing which is IQ. So VQ will be minus of IQ, the resistance of this winding. I am assuming that the resistance of these two windings, since these two windings are equivalent, only the spatial angle is different, so the windings are having a resistance of RA. This is the armature resistance. Okay, RA plus LQ, and I will write IQ here so that this operator P can be used. Okay, this is the minus sign. What I am trying to show, this is the generated voltage. Okay, now let us write the motional EMF. Now to write the motional EMF, you will see that this is the south pole here being created by the field winding, and this is the south pole here which is being created by the Q axis winding. Now these two south poles will repel each other. Okay, so according to the repulsion, the torque will be in the positive direction, that is in the direction of the rotation that we are assuming for the generator case. Okay, so I will use a positive sign. Okay, so this is the motional EMF for the Q axis winding because of the current in the field winding. Now you can easily see that I have taken the inductance coefficient for the rotational EMF same as the constant inductance coefficient which I have used for the transformer voltage, since I have assumed a sinusoidal flux distribution. Okay, now let us try to write the motional EMF because of the current ID. Now the direction of flux because of the D axis winding will be in opposite direction as that of the field winding, so the torque will be in opposite direction. So the sign of the motional EMF because of this current will be opposite than that this sign. So I will write a minus sign here, and it is LD omega ID. So this is equation 2. Now again you can notice here that this inductance coefficient will be same which I will use in writing the equation for VD. So let us write for the D axis voltage. Okay, first the drop in the armature. Now you can see this LD is already taken in the motional EMF. Now this is the transformer EMF. Okay, now using the similar convention for these signs, I can see that these two signs will be positive. Okay, so in this way I have written three equations. First equation is for the field winding, second equation is the Q axis winding, and third equation is the for the voltage developed in the D axis winding. Okay, now let us see what happens whenever there is a fault. Let us say there is a three-phase symmetrical fault on the system. Already this is carrying some current. These windings are carrying some load current. Now let us say some fault has happened. So according to the constant flux theorem, the field flux, let us say it was psi f naught initially before the fault happened, should be equal to the flux, field winding flux, which is going to be just after the fault. Okay, let us say after the fault the current is D axis current is ID and the current is IF in the field winding. Okay, so it will be simply LF IF minus MD ID. Let us say this is equation number 4. Okay, so this value is not going to change in the just transition period. Okay, just during the fault, according to the constant flux theorem, since the field winding is actually a closed winding only. This is a DC source. Okay, so according to that theorem, for a closed winding the flux linkages cannot change instantaneously. Okay, now I will write an equation for the flux linkages of the D axis winding. These should also not change. These will be MDIF minus LDID. Let us say this is equation 5. Now you might be wondering why the opposite signs have been taken. You can clearly see that the flux direction is opposite. For field it is like this, and for the D axis winding it is like this. So that's why I have taken a opposite sign. Some books are showing that since the fault current is usually demagnetizing, so that's why I have taken a minus sign. Okay, now from this equation what I will do, I will write the value of IF. IF is equal to psi D naught plus LDID over MD. Let us say this is equation number 6. Now I will put this value here. Although this lecture is very mathematical in nature, but in the final ending of the lecture you will see that we will have the equivalent model for the synchronous generator during a fault. Okay, so psi f naught is equal to LF over MD into psi D naught plus LD ID minus MD ID. That is, I have put this value in the equation number 4. Now I will take this here common, or I will multiply both sides by this quantity. MD over LF psi naught is equal to psi D naught minus LDID minus MD square LF ID. This is equally plus. Okay, so this is MDLF over psi f naught is equal to psi D naught plus ID, I will take common, LD minus MD square LF. This quantity is actually the inductance of the D axis during transient phase. Since we have neglected the effect of the damper windings, so there will not be any subtransient effect. So directly there will be a transient effect only. Okay, so as of now what I have seen, that the transient inductance is less than the inductance which is there in the final stage, okay, or in steady state. Now let us say this is equation number 7. We will continue the manipulation of these equation in the next slide. Now let us continue the manipulation of this equation. I will put LD dash in place of this. So I will write it here only. ID into LD dash. Okay. Now what I will do, I will multiply the both side with omega. So omega will come here, omega will come here, and omega will come here. Now I will put the value of psi f naught from this equation. So it will come out to be omega md lf lf if minus md id is equal to omega psi d naught. Omega is the RPM in radian per second plus omega id LD dash. Now omega LD dash can be written as XD dash, that is the transient reactance, but we will do it later. Now from equation number 2, we can see that VQ. Now before writing the equation for VQ, what I will tell you that there is one assumption that the resistance of the winding is negligible and during the transient the speed remains constant. Although these two are practically very near to this assumption, since due to inertia the speed will not change instantaneously and the resistance is also negligible for the windings, so we are very close to the actual scenario also. Okay, so VQ, now this d dt will be equivalent to 0 only, so this term is 0. So VQ will be simply md omega if minus ld omega id. So I will write it as equation number 8 and this number as 9. Okay. Now I will try to expand this. You can see that LF will cancel out, so it will be omega md if minus omega md square LF id is equal to, now this is omega d naught and this is id dash plus xq, xd dash. What I am doing here, xd dash. Okay, id into xd dash plus, what is this? This is the voltage which was initially in the d axis, omega d naught, omega into psi d naught, which is just VQ only. You can see here directly. Now I think that I have gone too fast in explaining why this is VQ. Now VQ, as I have told, can be written from equation number 2 to here. Okay, so this is nothing but omega is common, md if minus ld id. Now you know that md if minus ld id is nothing but psi d naught, so it is omega psi d naught. So this is VQ is equal to psi d naught. So this equation is simply written as RHS is VQ plus id xd dash. Okay, So now I think I have clearly explained how VQ has come here. Now in the next slide, what we will do, I will write this as we have seen that LD minus MD square over LD is LD dash. So this thing MD square LD can be written as LD minus LD dash, or this equation number 10 can be written as omega MD IF minus omega LD minus LD dash ID is equal to VQ plus ID XD dash. Let us say this is equation number 11. Now we will further manipulate this equation and we will try to make a phasor diagram out of it. Now we will further continue the manipulation of this equation. Now what is this thing? This is nothing but the voltage developed in the winding when there was no current in these windings. That is, ID was equal to 0 and IQ was equal to 0. That is, there was no load. Then the voltage developed in this winding in VQ when this current is 0 and this current is 0. So this is the only voltage developed, MD omega IF. So this is the no load voltage developed. Okay. Minus ID omega LD minus LD dash is equal to VQ plus ID XD dash. This is equation number 12. Now this LHS, as we have seen in our previous slide, was nothing but psi F naught into omega MD over LD. Okay, so if I write all this thing as, let us say, some quantity EQ prime or EQ dash, then if these flux linkages of the field winding are constant, then this quantity is a constant. So you see that whenever the machine is loaded, then instead of using the no load voltage, it may or may not remain constant, we should use a voltage which is equal to EQ prime, which is actually equal to the no load voltage minus ID into XD minus XD dash. Okay, which is nothing but, let us say, it is EQ prime. Now first of all, I have shown up to this point that instead of using EF for the equivalent model of a synchronous generator on a fault when it was carrying some current earlier, we cannot use EF. We should use some other value which is EQ prime, which is nothing but the no load voltage minus some quantity depending upon the load current and the transient reactance also. Okay, so we have got a clue here that something will be there which is depending upon the load current as well as the transient reactance. Okay, now in the next slide I will make a phasor diagram and we will further see that how this thing EQ prime is placed with the other voltage, let us say E prime, which is nothing but EF minus IA XD prime. That we will see in the next slide when we will draw a phasor diagram. Now here I have drawn a phasor diagram for the synchronous machine. The phasor diagram is very easy to draw. I can draw it again here. What I will do, I will show two axes, the D axis and the Q axis. Let us say this is current ID and this is current IQ. These two will form a current IA. Let us say this current is having a power factor angle theta and this is the terminal voltage VT. Okay, now VT plus ID XD plus IQ XQ will give me EF. So here this is the EF. EF is nothing but VT plus ID XD plus IQ XQ. Okay. Now this angle is delta. Okay. So VT sine delta will come here. So VT sine delta is VQ. Okay. Now what I will do, I will take a portion which is equal to ID XD dash. Let us say it is like this here. So VQ plus ID XD dash will be simply EQ dash, which we have derived in our previous slide. So this quantity is EQ prime. Okay. Now what I will do, in this VT I will add this same quantity. Okay. So IA this is ID XD dash. ID XD dash. What I will do, in this VT I will add a quantity IA XD dash. So IA is here, so perpendicular to it I will add a quantity IA XD dash. Practically we will find that on adding IA XD dash, the resultant voltage which we are going to have, let us say, is EI dash. This is EI dash. This is IA XD dash. Okay. So IA XD dash, these two voltages EQ dash and EI dash, EQ dash and EI dash are having approximately equal magnitude. Okay. So this phasor diagram is again giving me a hint that instead of using EQ dash in the equivalent model where EQ dash was nothing but VQ plus ID XD dash, I should use another voltage EI dash, which is nothing but VT plus IA XD dash. So this thing is being given by the phasor diagram. It is suggesting this thing, but let us verify it from the power side. That is what is going to happen during the transient to the power. Now, power in a synchronous machine is given by VT sine delta into ID plus VT into cos delta into IQ. Okay. This equation we might have studied during the study of this synchronous machine, the salient pole synchronous machine. So now we know that VT sine delta, this is VT and this is VT sine delta equal to VQ is nothing but, sorry, this is VT, so this will be VT sine delta. This quantity will be VT sine delta. Now from this phasor diagram you can see that it is equal to IQ XQ. Okay, so IQ is nothing but VT sine delta over XQ. Let us say this is equation number, this is A and this is B. Sorry. Now we also know that ID can be written as EQ dash, this is EQ dash, minus VT cos delta. Now this VT cos delta is nothing but VQ. So ID XD dash, EQ dash minus VQ will be ID X dash. So I will divide this by XD dash. you can see that EQ dash minus VQ is equal to EQ dash minus VT cos delta is equal to ID XD dash. So divided by XD dash give me ID. So this is equation number C. Now from B and C I will put the values in A. What I will get? P is equal to VT sin delta into VT into EQ dash minus VT cos delta over XD dash plus VT cos delta into VT sin delta over XQ. Now you already know that sin 2 theta is nothing but 2 sin phi cos phi. Using this identity I can further simplify it as EQ dash VT over XQ XD dash sin delta plus 1 by XQ minus 1 over XT dash VT square sin 2 delta. Okay, over 2. Now we have got the power during the transient using the simple equations which we have derived in our previous slide and from this Phasor diagram. Okay, now we know that for a typical machine XQ is actually greater than XD prime. So you see this quantity is actually negative. Okay, so the P is somewhat less than the total quantity. Okay, so if I use EI prime in place of EQ prime, let me erase this. Now in the power equation, if I use EI prime instead of EQ prime, then I will have to use this angle EI prime into VT sin delta I. So this is having approximately equal magnitude with the EQ prime. So this thing will remain same. Only this thing will reduce. Okay, but this reduction will be compensated by this negative term. So what I will do, I will just write the power in the transient during the transient for this type of machine by this equation. Okay, now this is again a hint. Now first hint was here and previous hint was clearly that we cannot use EF during the fault. So this is giving me a hint that this is the power in a network which is having terminal voltage VT and EI prime and a reactance XD dash. If it is angle delta I, then it is angle 0. So for this network, this is the equation for the real power. So from the power point of view, what I am seeing here, that if I, instead of using this full equation and I take this approximation, then again my power value will not change by very much value or by very much quantity. So my calculation or my model will still be okay if I use EI dash instead of EQ dash, which we have derived in the previous slide. So in this way, I have got an equivalent circuit model for the synchronous generator in which only XD dash is being used instead of XD minus XD dash and other things. Okay, and a voltage is being used which is nothing but VT plus ID XD dash, sorry, IA XD dash. Okay, J is for the reactance part only. So you see that the equivalent circuit model for a synchronous generator which was having some load initially and it went to a fault, symmetrical fault, we can see that we can use a model in which this is the voltage source and whose value is actually dependent upon the load current IA flowing initially before the fault happened, and the transient or the subtransient reactance. If I am also taking the effect of damper windings, then it will be XD double prime, that is subtransient reactance, and the terminal voltage which was there before the fault happened. So in this way, I think I have proved now that the equivalent circuit model for a synchronous generator during the fault when it was carrying a load initially is this. Instead of using EF, I should use another value which is dependent upon the load current and the transient reactance and the terminal voltage. So I think now this will clear the doubt for a lot of students who want to study in depth this topic. Since this coverage of the topic is usually not given in the books because it is not actually up to the level of the undergraduate students, so I think that the students who are willing to sacrifice their time and want to really understand why this model has come should see this video. Okay, so if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.